Near the mic, possible. That's a good question. I don't know. Probably no.
I got good news. You got a lot of holes to drill.
Yeah, that might be. What did you need to do?
I was gonna say. What? You still on the clock? You better be talking hours right now.
Oh no, like literally, because we understand your microphone.
It's very fun.
Have
you done software design?
How did you not see me?
Oh, okay. So you
want to go over the agenda or you want me
honestly, I like lazy boys. I find the one who sits down and goes. I did my thing like immediately.
So, the clicker.
Yeah, I don't know why you thought that.
Yes. All right.
We did several times.
Ah, frick buns. All right. Good morning, everyone. Welcome to the last major design review of the competition cycle. You lived. I know that was hard for some of us. All right. So our general agenda, we're starting off with yours truly going over high-level stuff with the robot, just a review of the competition, etc. Then we go straight into Max and Nate with systems, going over ConOps, TPM, our general requirements, analysis, etc. Then for the next hour, we jump into our two mechanical teams. So we break for lunch. Then we go through the rest of the club, software, firmware, P&H. Then we will wrap it up at about 2 o'clock and hopefully be out of here around 2:15. I can read. All right. So, as you all know, this year the NASA's competition has changed from a general mining competition to a construction/material moving competition. So we need to navigate through an obstacle-filled field in order to make it from the starting zone, which we are placed in a random orientation, to the excavation zone and construction zone, where we actually score points by constructing the berm. We need to follow NASA system requirements throughout NASA's systems engineering requirements throughout this entire process. So all of our documentation and the reviews that we're currently having. So for the general competition, we generally have two different phases. The first is our orientation phase, where in the starting zone, we spin the robot around in order to find the APRO tags placed on our construction zone that navigate to the excavation zone. Then we enter the second phase, where we begin our mining our straight line paths in order to collect material to then bring to the construction zone and build the berm. Right. As you can see here, each pile shown contains about 30 liters of regolith, which the initial requirements from NASA to get points was about 25 liters, I believe. So you can see how big that sort of pile needs to be. How many cycles that's going to take in order to collect will be gone over later in the X-Step slides. So, I'm pretty sure. So, for the full robot, our overall length is 1.14 meters, a height of 70 centimeters, and a width of 65 centimeters, which, fortunately, are all within size limits of the 1.5 by 0.75 by 0.75. Our mass is just over 50 kilograms, which is higher than PDR and likely still not a perfect estimate because, of course, when wiring and adding hardware, some of those are just not possible to put into top level assembly. Yeah. But this is a decent estimate for about where we're going to be overall. So with that, just quick review of everything. Head on into systems and Mr. President.
All right. So for systems, we'll go over first the concept of operations. This is essentially a flowchart that goes over how the robot will behave and operate, expected to perform throughout the competition. So this is the start of the concept of operations. At the startup phase, we're ensuring that the router is plugged in, we pull the e-stop, making sure that everything is set up, and this is pre-competition procedures to make sure that we're ready to get the robot started. After that, we go into the starting ascent phase, and this is where we extend our linear actuators at 100% power. And from the linear actuator current, there's a route there that goes, if it stalls, then we'll go into an emergency mode, but if that doesn't happen, then we go into the initial mapping phase. And so here, the robot does a 360 spin, and it searches for April tags. Then it sets a target to the excavation zone. From there, we go into the initial mapping of the area. So we just did that, sorry. We go into traversal of that path, and then it checks if it's close to the target, and then goes into the excavation location selection. So it does, okay, so from if it's close to the target, then it does that. If it's not, then the SLAM goes and navigates there. So if it finds a suitable location and we choose to set the target at the suitable location, if it's at a suitable location, we go into plunging, which is where the excavation goes into the ground and digs up the regolith for us to deposit. And then over here at the side, there's in case of a shutdown, there's a small little flow for what happens there. Down into the plunging. Once the robot has plunged into the ground, it can then do the trenching, which just drives forward and collects that regolith for us. After that, ascent picks up the excavation system and then goes to the berm. So that's the traversing to the berm area once that has been complete. Following that, if it's at the target, figures out whether it's at the target for the berm, and then deposits it using our auger system. So that was the general concept of operations for how the robot works. Software will go into more detail about the autonomous portions of it in their section. With that, Systems has done an integration report, so based on the integration risk factors that we've identified from PDR, we've taken a look at these and looked at to see which ones are at risk for our upcoming robot build. So first threat is miscommunication. We've identified that as a low risk. Threat number 2 is lost, unclear, or non-existent documentation. We've identified that as a high risk because we have yet to complete the full manufacturing plan at a sub-team detail. Currently, we only have one for just the general of how the manufacturing phases will go for each of the sub-teams, but not necessarily the assemblies and parts. So this is something that needs to be remedied as soon as possible after CDR. Threat number 3 is misinterpretation of system or task requirements. We've identified this as a medium risk. Some documentation content that was done with some errors, but that was addressed and teams are aware of that. So it's a slight risk there. Threat number 4 is forgetting or missing deadlines. This one is not a risk. We've been keeping track of the deadlines pretty well. Mismanagement of resources. So basically mismanagement of resources for people, for materials. We've identified that as a low risk for our general resources for members and for materials. There are some concerns with VIP members and they're helping them contribute, but overall with just directly contributing to the robot, that is a low risk. Shift in project focus or revisions in the rules. So this one is basically, are we keeping track of NASA rule changes and are people keeping in touch with the rules? This is medium risk because referencing back to the rules is generally a rare thing to do just within the sub-teams if you're not a sub-team called systems, but the sub-team called systems keeps track of this on a somewhat regular basis, and usually these rules don't change too much from NASA, and we are aware of that if it does, and it's communicated. External roadblocks, so that is identified as a low risk currently. And then design issues, that's a medium risk, partially because of that late manufacturing plan. So this is the current state of our risks for continuing and integrating the robot. So real quick, what to expect from systems going forward now that we've basically finished up our CAD and we're starting into that manufacturing phase. Most of that work will be handed off to FabOps to make sure that manufacturing is done properly. But systems, as a sub-team, we will be entering our systems engineering paper writing phase. So for a lot of our members, this would be gathering that information, making sure we have everything ready to write that paper. And so some of our members might be asking a bit more questions or just asking to dig through some older documentation so we have something to put into the paper. There's also the internal design review of parts that is yet to happen for some of our components going into manufacturing. So for the chief, president, and me, we will be looking at that. So that's part of systems tasks that needs to be gone through. We'll also be keeping track of our manufacturing and testing schedules, just making sure that we're not slipping behind too far, and if we need to address certain issues. Overall, just keeping a healthy pulse on where we are progressing and getting towards that proof of life. And of course, keeping tabs on the real robot TPMs. We have our estimated ones based on our CAD, but we'll need to make sure that our real robot also fits the NASA requirements. That's arguably the most important part. And so we'll be keeping track of that as parts are built and we're assembling things. All right, and now we'll go into our expected performance with our president.
So basically all the information that I share and all the calculations are done primarily based on a lot of previous years' data. So our traversal rates that we saw last year are what kind of used to come up with our estimates for our driving speeds and our trenching speed, which our trenching speed is just a current estimate of how slow we think we're going to have to move when doing our trenching. Based on this, kind of the major changes from CDR is we have a bit more conservative estimate on our performance based on both how big of a trench we think we can make, because we have to find an area that avoids obstacles when doing that, and also our deposition storage, estimating more conservatively, is closer to 6 liters. So with that into account, the estimated per cycle collection is 6 liters, which is a 0.7 meter long trench, and that is why our performance has gone down. Our previous estimate was about 10 or 11 liters, but by doing that, that reduces our X-step cycle time to closer to 3 minutes, and therefore we can get an extra, just the way the time works out, we should be able to get an extra cycle, possibly, hopefully closer to 3 cycles during the UCF run, which is a 50-minute run, and closer to 7 or 8 during the KSC run. All right, so here's the pre-operation score. The biggest changes since PDR, is due to our 8.5 kilogram increase in mass, which was mostly some small design changes, but mostly adding fasteners into the assembly. We do lose significantly more points during pre-operation, and our autonomy targets are still as they were, so we're hoping to at least get traversal autonomy on one of the attempts, and either excavation or dump autonomy, and that gives us an autonomy score of 250 points. As far as dust tolerance go, again, not much has changed since PDR. Right now we have only, except for the fact that we've implemented a lot of the things we talked about. So, for example, like Drivetrain, all its components are now, should be, have dust covers on them to prevent any regolith to getting into the chain and gears. So that awards us 10 points. And then the question is our current mining mechanism, where instead of last year where we spun the buckets the other way, spinning them backwards, going to be dust tolerant enough for us to get awarded the digging without dusting tolerance? Right now, I'm saying yes, but that, of course, is up to the judge's decision. We haven't pursued any custom dust sealing features, which could get us extra points, as well as any active dust sealing. That has not been in the scope of our design process currently. But you can see by how much, when I move into our performance thing, how much these extra points could benefit us if we were to have some extra time in comparison to trying to increase some performance. So here's our berm building estimates. So like I said, at the UCF, estimating it with a 3 cycles, so 18 liters. These are in meter cubed. And at KSC, hoping to get 6 cycles. Is that 48? Sure. 8 cycles, right? 8 times 6. So our points from our previous estimate at UCF has actually stayed relatively same, because if we mine for a short amount of time, we should be able to get 3 cycles instead of 2. And that's why, even though our performance has gone down, still estimating we can get roughly the same amount of points, because we'll mine the same amount because we have an additional cycle. While KSC being longer, that performance hinders us more per cycle. So those points went down by about 13. They were about 70 points at PDR. And here's that overall comparison between our totals. So about 60% of the decrease in points, about 100 points decreased for NASA, is due to mass, and about 40% is due to a more conservative estimate of performance. So you can kind of see how much mass does affect us in comparison to performance. And like I said, so like those dust tolerance features that we are currently not pursuing, that could give us an extra 20 points, while looking at increasing performance, that's only 2,500 points per point. Like, it's so if we did like an extra cycle, this would raise it about the same. It would be about, what is that? It would be an additional 30 points on the UCF. So that's an additional whole other cycle in comparison to just adding some additional design features. And the other part, expected performance, another kind of view looked here is what happens if we attempt autonomy, and how many points do we get there versus trying to the most skilled operator. So even assuming that we are 3.5 times better than autonomy, that is the kind of the level we need to be, about 3 times for KSC, but you can see that that's how we get kind of similar points. And then UCF was still, even if we're 3.5 times better at collecting material, at UCF we're still not approaching beating if we successfully do autonomy. And this is also one of the big limitators there is our storage on deposition, because that cycle time is going to still be quite significant, even when we're doing manual control. And lastly, just to give you a perspective of what that decrease in trench length looks like. So on the right here, we have our PDR 1 meter long trenches, and now we've reduced those to 0.7 meters. So we feel this is not only more reflective of our capabilities, but also much more reasonable to be able to trench for only 70 centimeters in comparison to the 1 meter, because we have to find an area that is avoiding obstacles to be able to make those trenches. And I believe that is it from systems and me. If we have any questions about, yeah.
So if you go back one slide, so you have to do like more than like 2-3 cycles. I'm not sure if you'll be able to drive straight necessarily. You might have to do like a curved path in order to dig. Is that something that would?
Correct. So we would ideally like the trenches to be the robot driving mostly straight. That doesn't have to be like a straight line this way. It could be like straight this way. But right now, to find the optimal excavation area, at least from what I've talked about with Isaac, we want to keep them like once we start that trenching, that should be pretty much a straight drive controller, just so we don't risk like overturning and getting the wheel into the trench-ish. If that makes sense.
I agree with that, but I'm still just like, because first 2-3 cycles I think that's reasonable. I think after that it's like it'll be kind of hard without having some curving to get mining if you want.
Correct. Yeah, I think at the Kennedy Space Center when we're trying to do like 7 cycles in 30 minutes, right? Where are we gonna put all those trenches is like, probably a very valid point.
If there was some sort of way to understand what the quote unquote like max angle we could turn at is, that'd be useful, because that can even help optimize previous routes where we go like 5 degrees turning and then we do 5 degrees turning in the other direction next time, and we're using less area to get like 2 cycles instead of 1 per se.
Yeah.
Wouldn't that be based on the system we create though? Because we're inputting, like we're creating the robot's code for movement. Wouldn't that have to deal with how the robot moves then?
Yeah, that's fine. I don't know what the mechanical restraints are.
Yeah, and I don't think we do either, really, if we're being frank. So that might be something that we should add to any, like, when we get to testing, is to be able to try to establish, like, how aggressive can we turn. Or maybe we can do, like, the robot turning while digging, and it's, like, there's no risk of, you know, autonomy, like, overturning and going into the hole or something like that.
Okay.
Maybe that's something we just need to make sure we test and be able to establish. From a software perspective, how difficult do you think it's going to be able to find places to trench, right? Because it's not just find an open area. We have to find an open area where we have a place to trench, and then also not go back to the exact same location before.
Yeah.
Do you see significant difficulties in performing that autonomously?
I don't like have a solution
Yeah.
off the top of my head, but I don't think it would be too. I think like if you're trying to do just straight line paths, it's like pretty straightforward. I think if you're trying to do quick paths, which is something I think we should attempt, I think that's a more complicated problem. I'm not 100% sure. That's more of just like a kind of have to do some investigation on that.
Okay.
But yeah, I'm not 100% sure.
Yep.
Can you go back a couple of slides?
Yep.
I think it's to the point, yeah. Is there, the construction points for non-choosing teams, is that just based off of location? Because I saw that the points were different.
Yeah, so at UCF, I honestly have no idea what this is about, because at UCF, they are awarding 1 point for every 100 liters of regolith collected, which is a lot of regolith. And that's basically the way they're doing this is this will establish whether we get to NASA, to go to NASA. So we have to be in the top 10 based on this scoring, unless, of course, we get first, second, or third, and that's based on the overall score. But to be in the top 10, it's only based on this, is my understanding. So we are scoring very low at 0.63. But the question is, like, why, like, if other teams are going to be able to collect, like, 100 liters of regolith, which would be a lot from at least our design, would be very difficult to collect that much with our current design.
I find it interesting that they put such, I mean, it looks like they put a very low emphasis on actually collecting the regolith.
Correct. Yeah, it's much, like, that's why, like, getting autonomy points is so much more valuable than being really good at collecting, because the scoring is guided that way. And even, like, dust tolerance stuff, that's a lot of points in comparison to, like, making the system, like, a 30% more higher performing.
Yeah.
Pursuing dust tolerance is almost the same effect.
I'm really surprised. Okay.
Yeah.
It's because dust tolerance, it was like 75 points for
There's-
one of them,
Yeah.
which is equivalent to like 7.5 cubic meters of regolith, which is absurd.
Yeah.
I do find it surprising because you're in a competition to build a mound, and then
Correct,
you're
yeah.
making a dust tolerance cover more important theoretically.
Yeah. Yeah, because like these, even like transferring crushed basalt without dumping the crushed robot basalt on your own. So that's something that we've talked about briefly of building out more of a cover between the transfer excavation deposition. And that could get us a lot of points, but it's just something we haven't got to yet.
I think it's just important to understand that like the points are really dictated by like what NASA's like kind of valuing. So like dust tolerance is like kind of rover lasts for like a year or so. Even
Yeah.
if it's less efficient, if it can run like continuously autonomously over that entire time, that's more valuable than something that will break after like a week, even if it's 10 times more effective.
That's fair.
Any other questions before we move on to X step? Yeah, Nicole?
Can you go back to the map slide?
Yes.
Yeah, that one. So are these red dots expected locations of obstacles, or are they just sort of random?
Yeah, so they're completely random. The darker red is the craters, and the lighter red is the thing.
So have you considered, like, if you have to mine and then go over an obstacle to then drop off in the construction zone, how much additional time that might take you?
So in the short answer is yes, but not very sophisticated. So, you know, this is, if there was no obstacles, this is 3 minutes as our estimate for how long it would take. I've added an additional time for each cycle of 1.5 minutes for any repositioning, any going around obstacles. So yes, but not very, like, that's purely based on intuition, if you will, not necessarily based on any sort of testing or any sort of data.
Right.
So
Is your autonomy speed the same speed as it would be if an operator was running it?
no, so we would expect we could go our max linear traversal speed is 50 centimeters per second.
Yeah, that's about right.
So we could probably approach, you know, if we're averaging out, like this traversal speed is an average of us avoiding obstacles at the Alabama competition. So I would think we could get up to like 30 centimeters per second traversal. I don't think I have it on here how much time. The trenching speed would probably stay relatively the same.
Right. Yeah, that makes sense.
But that is a good point that I don't think that my skilled operator calculations are truly adjusted. They're just I don't know exactly off the top of my head how the time works out between like how much time we're spending extra mining versus driving, and how if we're driving, you know, what's that, like 5 times faster, how much that time savings would be better for that. So that's something I should probably follow up and redo, so make sure those calculations are aligned, that skilled operator autonomy is much better than a skilled operator. So that's a good point. Any other questions? Yep.
When we test the robot, do we usually like time like certain runs and then adjust these calculations like as we go?
We don't usually have calculations. Theoretically, that would be our intention. So
Okay, like time the same
I would like to time it, and we now with updated data acquisition stuff, we'll have a much better recording system and visualization for our data. So the intention would be before we go to competition to adjust these expected points. based on our actual testing data and our actual traversal times and our actual mining performance. So if we find we can trench at twice the speed, I want the expected performance to reflect that. So that way we kind of know where we sit when we get to Kennedy. Yeah, Grant?
This might be a silly question, but is there a reason we believe a skilled operator would be significantly faster? Like, or why is that? Like, it's like, do you think they align quicker than the autonomous program?
For traversal, yes, that is the general assumption. Is because of the speed it takes the robot to like localize itself and map and plan a path. A skilled operator is not going to have to do that because they have eyes. But also things like finding the APL tag in the beginning is going to be not necessary for a skilled operator. And so it's generally thought that a skilled operator would be faster given our current state of autonomy. Yeah. Okay, I'm going to move forward on to next step.
Hello, it is time for the excavation-deposition. Yes, that's the mouse. Yep.
Some important terminology just to understand like what we're talking about. This here is driving configuration where excavation is fully raised, and then mining where it's fully lowered, and starting configuration is kind of in the middle to remain in that overall boundary box. Some mass calculations for XF based on the current like CAD with all the fasteners and stuff. Significantly lower than last season because it's a smaller system with a less complicated actuation system. So excavation is a little bit lighter overall because it's shorter. Deposition's a little bit heavier because it's an auger and a bit larger of a system overall, but it is also static. Also, different motors and stuff can affect that. And actuation is just kind of gone. It's rolled into excavation because it's just the 2 linear actuators instead of a whole extra system to actually go up and down. Going on to excavation specific stuff. Again, 14 kilograms with everything included. And then these are kind of the general things that we're going to go over. And this is the overall look of the system that we're talking about. The structure of excavation is these 3 tapped rods that will be screwed in on the 2 plates. There's also linear bearings on the structure plate and 6 rod clamps, 3 at the bottom, 3 going to the top plate. And then there's a single plate at the bottom and the top. There's a plate going around the bars here, and then the overall structure that holds it all. The actuators are on the side of the system. So this is the mining configuration where it's fully lowered, and then this is the driving configuration where it's fully heightened. So with that, we're able to do current sensing to detect when it's at the limit, upper and lower, and then for the midpoint starting configuration, we'll just do that manually because it's just easier that way, and we don't have like a specific distance necessarily set for that. And then also the way this linear actuator mounts through the plate, it basically goes through the plate and there's a little hole going through it, and that will be a pinned connection to prevent it from coming up because the system will weigh down on it at all times. The way we're going to tension the system is called the pancake tensioner, which is the 3 rod clamps will go into this bottom plate, and this plate above it holds the actual drum. So as you tighten these and clamp them together, the overall length of the system will increase, which will tension the belt. We plan on having these screwed into the rod clamps, and then this plate will be threaded, and you can tighten these 2 screws to be able to tension the overall system. And then after you apply that tension, then you screw down the clamps to be able to hold a lot more of the weight. more reliably. As for the scrape plate, which is one of the big design changes this year, instead of the buckets going kind of upwards, they're going to be going down into the ground and then up along this scrape plate. So this kind of changes some stuff. It simplifies the bucket design because you can have more of an open face bucket with just small little sides. It's going to be about 3 inches, 4 inches into the ground for mining depth, which is a lot lower than previous years. So some concerns with like this kind of being submerged in the ground might be a little bit lower than previous years, but it's still something that we're going to be looking at when testing. The buckets are about 4.5 inches wide, which allows us to collect an adequate amount per trench. And then the way this scrape plate is actually attached is through a screw at the bottom and then a slot at the top to allow for the tension to lengthen and contract this system. The actual bucket design is very simple, just 2 little brackets on the side of an L channel that will go onto the belt. And we have a lot of these to make, and depending on our testing, that could possibly be modified for increased volume throughput, but that's really like probably not going to happen. This is like the design that we're sure is going to be gone forward with. And making a lot of these, it's good to have it be simple. So, yeah.
And that brings us now to talking about the deposition system. So for system overview, this is the deposition system. Mass estimate is about 5.6 kilograms. That's including fasteners and metal and whatnot. It's going to be spinning at about 34 RPM and producing about 28 Newton meters of torque on that auger, which through some downscaling calculation should put us in the range of an acceptable auger torque for the size that we have. And then, of course, there are basically 2 parts of the system. There's the auger, and then there's the bin that the auger is in. So talking about the structure of the structure of the system, it's held together by a bunch of these 1 by 1 inch L channel connectors, which are really sort of holding everything together, and then also these 2 1/4 inch plates that are just going down the side. They're sort of holding it all together. And then we have there are 2 2-inch by 2-inch L channels, one at the front and one at the back, and those are what the system actually mounts to the frame, and that's what connects it to the rest of the robot, just to give some structure. And then we're using a bunch of number 10 bolts, a bunch of number 10 bolts to connect to all these 1/4 inch panels, which we have throughout in order to hold the system together and make sure that it's structurally sound. And then we're going to be using rivets to connect these 1/16 of an inch side plates to these small L channels as a weight saving measure. And so here we have some conservative deposition storage volume. It's about 5 to 6 liters. This is the big limiting factor here, and why these are such conservative estimates is because, as you can see, we're basically imagining that the regolith just sort of piles up in a static mound, as opposed to being dispersed throughout the system in a more even way, which it's entirely possible that it does behave like this, or the vibrations of the robot might cause the dust to settle in a more flat manner, which would increase our deposition volume. And also we could try a programmatic approach of spinning the auger occasionally while we're running the excavation in order to try to shake up and sort of flatten out that mound. But these are, of course, very conservative estimates, just so we have a baseline of what to expect from the system. And they go from assuming we get 1 inch or whatever to assuming we get like a 3-inch wide on the top mound there. In terms of mounting, as I said, it mostly connects with these. It connects to the frame with these 2 by 2 inch L channels. So on the back of the robot, the L channels have 2 strap hinges on. which are mounted to. This is a not fully updated picture. In the current CAD, there are bolts, and that connects this L channel to the strap hinges, which is on the back of the drivetrain frame, and then these are going to be held in with riv nuts. So that we don't have to have bolts going all the way through the drive frame, which we'll be talking about more in drivetrain. And then at the front of the robot, we have these two 20-kilogram load cells, which are held off the frame by spacers in order to allow them to actually bend in the way that load cells need to for them to detect the load. So they're held on the front here, and then on the back. And then on the back of the load cells, we're going to have. I tried to put these in the CAD, and it crashed twice, so I didn't do that. But they're going to be 30 millimeter M4 bolts that we're going to screw up through the holes, and then the frame will just the deposition will just be resting on those bolts, which isn't as rigid as we would like. But also for the load cells to function and for us to be able to detect the deposition capacity, which is of course important for autonomy, it needs to be able to bend. The deposition needs to be able to sort of rotate back and forth, which we've tried to provide rigidity to through the strap hinges on the back. For the motor, we've got two sprockets. The 34 RPM is achieved by gearing down the given motor with a 100 to 1 gearbox, and then we put a 22 tooth number 25 sprocket on that, and then we have another sprocket on the auger for it to turn, and then to tension it we have this idler sprocket, which is just on a pin, and you can't see it in this straight on photo, but there's sort of the idler isn't in a hole, it's in a slot that sort of goes like this, and so in order to tension it we can just loosen it at the bottom and move the pin around that slot in order to make sure that we have the correct amount of tension on the chain. And then for the DFMEA for the deposition system, we've gone through it. The highest risk priority number we have is 28, mostly because we think that we can either easily detect features or they're not very likely to happen. So the biggest risks that we have are the load cells overloading, which could cause some deformation or maybe even snapping and failure, and then the entire deposition would just buckle, would just swing down, and that would be problem. Although we can probably get more load cells or swap load cells out for just like a bar or something at competition, so it wouldn't be fully debilitating. And the way we're going to, but that's probably not going to happen because the deposition's estimated mass is 5.6 kilograms, and we're only expecting to get about 6 liters of regolith, and we have two 20-kilogram load cells, so that's 40 kilograms max. So that shouldn't be an issue, which is why we don't think it's likely, and of course we would very easily detect that. And then for the hinge mounts, if those get misaligned, then it could cause deposition to maybe not be able to fall, or just might cause it to sort of buckle and bend in some other way. This is almost impossible though, because the hinges are we have like 6 bolts in each hinge, so they're going to be locked down real solid to the frame. Manufacturing plan for deposition, we're going to be laser cutting these big 1/16 of an inch side walls and the front wall because those are just 1/16 of an inch aluminum, so we're just going to be laser cutting those. And then we're going to be water jetting all the 1/4 inch aluminum parts, which are the side plates on both sides, and then the 3/4 inch gussets spread throughout. And then the bottom tube for the auger is a PVC pipe that we're just going to be cutting in half with a bandsaw, and then we're going to have to do some other cleanup work on the ends to get it to fit in properly. And then the L channels are just going to be cutting to length and then milling them in order to get the holes where we need them. That's it for the excavation X-Step presentation. Are there any questions? Yes.
If you could create, like you were talking about, it's possible if it, or through testing we could see if we could fit a lot more regolith in the deposition system. Would we consider digging a longer trench then, or would it still stay at 0.7 meters?
We might, that's sort of the thing that we'll have to play by ear when we see the testing. It might be that we see, oh wow, actually, each trench gives us a lot more regolith than we expected. So, or we get more regolith per meter trench than we expect. So, yeah, a bigger deposition can, does mean that we can dig a longer trench, or we might get there and realize, actually the trenching is sort of the limiting factor on the system. That's just something we're going to have to figure out when we actually can test the robot.
Maybe this is something that I should have asked earlier, but when you're going in to get the regolith, is the stopping factor from the buckets moving to get into the auger, is there a point where it hits the bottom and then it stops, or is it based off a time amount, and then after a certain amount of time the robot just thinks the system is complete?
So for knowing when it's full?
Knowing, that's what the load cells are for.
The load cells. Okay.
So we're going to be getting current from the load cells. We're getting data from the load cells, and we're just going to be waiting for a mass.
Mm-hmm.
We're just going to be.
Also be experimentally determined for what set value we consider is go to deposit.
Okay, and then could we go a slide further? I think. To where you're going to put the bolt. No, not that one. You're going to rest bolts on the.
No, that's this right. That's this one. So you can see there are two. You see there are holes. You're talking about the mounting for on the front.
Yeah.
Yeah. So you can see that there are holes in the ends of the load cell that don't have screws in them. What we're going to be doing is we're going to be putting a bolt up through these holes and then fastening it down on this end of the load cell. And then this L channel is going to be, if this is the L channel, this is the bolt. It's going to be resting on it like this to support it.
I almost wonder if you could redesign the bucket design, because then you could use your L channels to connect to both the load cell and the part. And then you could also have the L channels on an angle, so that way you could connect it that way.
Wait, what are the buckets?
The buckets. I'm not sure what you
So
mean.
you could redesign the ends so that the L channels are angled, so that way one part of the L channel is resting on the load cell and then the other part is resting on the frame, and then you could connect it that way.
Like excavation buckets? No.
Yeah, the excavation buckets.
I'm sorry. I don't quite understand what you're.
Overall view?
Yeah.
Here.
This is
Go to that one.
Yeah. Here's the overall view of deposition.
So this is the part that's resting on the load cell.
Oh.
So the overall deposition system hinges from the back of the robot and rests on those load cells, and that's just how it senses the weight from that front end.
Are you concerned at all about side to side rigidity, and is there a possibility of what if you added some countersinks into that L channel, so that way the bolt could have some back and forth rigidity? What was the
back and forth rigidity is something that we thought of. It hasn't been too much of a concern because these are fairly robust strap hinges that we're using on the back. So, but also we haven't played them, so I don't know how much there is. Countersinks is a really good idea, and I'm gonna steal that.
Yeah.
Is the load cell and the L channel there perpendicular, or is it an angle?
What on this?
So where the bolts interface with the.
It's at an angle, but a small countersink, not all the way through, would still provide some amount of wiggle room, or even a small blind hole could provide that.
3D printed cup could also work.
3D printed cup, yeah. That's something that we can. That's a small little feature that we can quickly investigate because that should be easy. Yes.
I'm sorry if I missed it. Is it still a plastic auger?
Yes.
Okay.
It is still the auger is still made out of 2 plastic flightings fitted onto a 1-inch hex tube, and then on the ends we have 1-inch hex shaft, which we're gonna put in, and then we're gonna turn them down to turn down the ends to 1/2-inch shaft to fit through bearings.
And you already sourced that from McMaster, the augers?
Yes, the augers are from the Lundell Plastic Corporation.
Oh yes. Okay, sweet.
Yes, Max.
So you said that the load cells, they have screws going up, and that's what will take the weight
Yes.
of the whole deposition
Mhm.
system go onto load cells.
Yes.
Have you done analysis to see if buckling would be a concern with the mass on just two M4 screws that are 30 millimeters?
Yeah, 30 mils long. We have not done that. We have not done that analysis.
I
I
don't imagine
I
even like 50 kilograms like going in the what's it?
the axial,
Whatever,
yeah,
like, in
the
direction of
screws.
bolt.
I don't know. Looking at it, it feels to me like the screws are going to be mostly axially loaded, which is the way in which they are, which is the way in which they're very, very, very strong. But we will run that analysis and see if that's an issue. For sure. Yes, Mike.
So if you have this thing on hinges
Mm-hmm.
and it were to flip up, what is the first thing that it hits?
It would flip up.
If, like, what is the maximum that it would go up before it hits something?
I would imagine.
It's P&H box.
It's either probably it would hit the P&H box, or it's possible that the dust cover down here might hit the drivetrain, the frame. That's just we could investigate that, but
Could you put like something?
We can
over
put like
the
a
L
cable
channel?
to the
No,
front
not a
end
cable.
or
oh,
something.
like over the L channel to prevent it from.
Physical something that stops it from hitting a wall.
That's what we were
Okay.
Yeah. We could investigate something like that. I don't know how necessary that is, just because I don't think there's ever going to be a force in the competition that causes it to flip up like that, except maybe, I don't know, I guess if we drove over a rock or something or fell in a crater, that could do it. So, we can investigate that a little bit.
Because I'm also worried. What is the ground clearance of your system?
Of a system,
Should
I think,
all be above the chain guards of drivetrain. It should be above that point for everything, including like driving for excavation and also like all
Yeah.
of the deposition stuff. should be above
deposition
that.
is, yeah, it has fairly good ground.
That question, could you go back to like the initial picture where you show all like
Then it's
where
gonna be
everything's
on
sitting?
you're gonna have
Guys,
a
I'm
vertical
trying to hear the conversation and I can't do that when people are talking. So
This picture?
fully like the first slide you said.
No, sorry.
When you showed it initially, the ground clearance on driving.
There we go.
Starting when
So this chain guard is like the lowest point on the robot you can see.
Yeah.
Right.
Yeah. So, the ground clearance on deposition is not a concern. Any other questions? Yes.
So back to the hinges. So if you're driving, are you concerned about it bouncing up and down and that affecting your load cell? You know, if you like are on a scale and you jump,
Yeah.
it makes the number a lot larger, and then you're gonna get all these readings that might not be correct. Are you concerned about that? Is there anything you're doing to prevent that?
I think that's more of a data cleaning thing with software, but it could be like you can normalize it over like maybe a 5-second period.
Yeah.
If it's consistently above for that time.
The answer is we're not hugely concerned because this thing weighs about, this thing weighs about 10-ish, 12-ish pounds or 15-ish pounds or so. While it's unloaded. And when it's unloaded, it weighs about 5 kilograms, and these things are collectively graded for 40. So there is a concern. I don't think there will be such a magnitude of velocity such that it overloads them. But we can try to remedy that problem with having some sort of system over the L channel to sort of limit that motion that Mike was suggesting. Yeah. Yes.
Just a point so I don't forget. One option we could bring it is the P&H box struts. They locate directly next to deposition, right? If you go to the overall. Is it possible we could put some sort of upper hot stop on the top there, and then that just interfaces with the top of deposition, basically?
Yeah, we could do that as well.
Basically,
There's
to
that hasn't been investigated very thoroughly, just because it's really sort of a quick thing that we would throw on there.
Just like there are potholes and stuff in the course, but like, unless it's a human driver, I guess, like really booking it, I don't think there's gonna be a lot of like up and down jerky movement that's like super energetic.
Yeah, especially
Pop-up a lot.
considering we have a traversal speed of 8 centimeters a second, I'm not sure there's going to be. I don't think there's going to be that much sort of jerk in the system unless we fall in a hole. Yes.
Are we worried about like a lot of regolith piling up on top of the P&H box if we were to run the bucket elevator really fast? Like, would it just
I think that's another testing thing, but if it is, then we'll just
like create
plastic.
Yeah, we'll just
like
put
a
a little wall there.
barrier.
Okay.
Yeah. But theoretically, the P&H box is far enough back that it all just falls into the deposition. Yes.
This may have been asked last time, but I don't remember what your response was.
Mhm.
Are you worried about binding on your linear actuation thing? Because isn't it kind of over-constrained if you have like 3 linear bearings?
I believe the linear actuators are like precisely controllable, so they should be able to be aligned. Like,
No.
Side to
But
side.
like the linear, the 3 linear rods and 3 linear bearings. like,
because
those-
it's
I don't
all
think we have the
water
tolerances.
jetted like plates, it should be very precise, like low tolerance. So there shouldn't be like misalignment from that. So it should be fully constrained where it's like not able to bind up in that way. Also, using this system in previous years, like unless we like really over tensioned it and the bars started bending, other than that happening, it wasn't a problem. But that's a good point.
And if we start getting worried that it might be a problem, last year we also made a system where we basically put a plastic sock around the lead screw that we had to prevent dust from getting into that. So if we are concerned about it, we can do a similar situation this year, and that's not too big of a problem. Are there any other questions?
To quickly answer the buckling of the bolts question, because I just pulled up an online buckling calculator, the load cell will fail a whole lot earlier than the bolt will even start to buckle. Like, the factor of safety is like 40.
Excellent. Oh man, we rule. Good job, us. Yes.
Do you have any vibration concerns from either the deposition or from the auger?
Honestly, we kind of want vibrations because vibrations will loosen the regolith and theoretically let us get more of it in a more even thing. There's not actually, in terms of like mechanical components, it's not that precise of a system, right? It's sort of just 2 sprockets and an auger. So, I'm not too concerned with it shaking itself apart, really.
Yes.
Alex.
Yeah. If you want vibrations, how stupid would it be to add a little vibration motor or something on the side?
We've discussed this. This has come up. Maybe not stupid, but probably stupid.
Cool.
There's not space in the P&H box for it.
There's not space in the P&H box for it. But we could do a similar facsimile by just like spinning the auger at a really low RPM as we're, even lower than 34. Spinning the auger, just slowly as or spinning the auger every 3 seconds, or just some little things there.
And in a reverse direction? Would that be something?
Spinning in the reverse direction would actually pull regolith. That might break something. Spinning in the reverse direction would actually probably press regolith against the front plate here, and into the bearing, and into a solid wall. And I don't want to do that. Yes.
So there should be a software stop preventing it from spinning in the other direction.
Yes.
Yeah.
Are there any other questions? All right. I think that takes care of.
Yes.
Yes. Sorry.
Earlier when we were talking about, or during the system presentation, when they were talking about dust mitigation, there were some mentions of like potentially some sort of chute connecting the like excavation system with the deposition system to prevent dust from falling off the P&H box. Is this something that you've seriously considered, or is this just more of a if we have time or if we have issues type of thing?
I think a lot of the dust mitigation ideas are kind of like dependent on what the system actually is now, because with the whole scrape plate, the way dust does go through the system is very different, and we don't know exactly how those mechanics work. But basically, like L channel.
Yeah.
And like it's a lot of like pretty simple potential add-ons after the fact that can be made, or like a wall on the PNH box, basically. Like,
Yeah.
it's all like simple, like either flat sheets or like small channels.
Okay, so this require a lot of like actual
Yeah,
engineering
and
work.
that's kind of like if it's necessary
Yeah.
thing, then we'll add it. But
The only thing
as
that-
of right now, we don't know that it's necessary.
The only thing that might be complicated is if we wanted to add like an actual chute, like a top cover chute for dust to get into deposition. But I don't think that's really something that we've considered. But that might actually take some doing. But everything else should be simple. Screw a piece of polycarbon or call it a day. Are there any other questions? Okay, I think that's it for X step.
Sorry.
Yeah, it can so imagine a rectangle,
I
right?
updated. We just gotta like X it out. That's a rectangle bed. You can measure that.
Yeah. That's the full thing.
It doesn't matter what the piece of paper says, what matters is in your heart.
It's like a little electrical heart.
You know the crucial difference between me and Poppy? I shower. You're talking, try to make it go.
They're strong as hell.
Yeah.
Okay. They're gonna make it.
I can't wish one. Alright, so we're at the drivetrain portion of the CDR presentation.
When you're talking, stand near your mic.
Okay, yeah.
Oh, so this is the drive system overview, and it didn't really change from PDR, so we're going to be using a chain drive system, and it's connected with sprockets on both the front and rear gearbox. It will be able to climb over obstacles that the software system cannot detect reliably, and it should be able to operate continuously for at least 30 minutes. And then with the frame, it's going to fit in that 1.25 meters long by 0.75 meters wide and 0.5 meters high volume, and it should be able to support 70 kilograms of load.
Okay, so first stuff that we're going to kind of cover is our post-PDR changes, which mainly fall under a couple of smaller redesigns. First things first, we redesigned our chain guard. Initially, it was just aluminum U-channel that would slot in between the gearboxes, but we decided to switch it to a more lightweight design. Can't really see it in this picture. Hold on, let me move back. It's a bit hard to see in this case, but now it is a lightweight polycarb design, which is going over the frame and gearboxes rather than sitting in between them. This is more as a bit of a weight saving thing, and then just to make the decimation a bit better rather than having a little bit of a press fit thing, give us more wiggle room. The big thing that was redesigned since PDR was the chain tensioner. So the current design for the chain tensioner is what's actually pictured on this slide, where, as you can see in this top view, it is going to be currently these are lengths, they're going to be switched to 3/8 aluminum plates with a brass rod through the middle and a small sprocket. This was designed in this way partially because most of the idler sprockets, the size that we found, were the whole size of basically bottom of the frame to the bottom of the gearboxes, which I don't want. That's not fun. So this design was designed with the fact that using the brass rod, we wouldn't have to use bearings, so it would just spin on. And the way this is being tensioned is it's not fully pictured in these designs 'cause they're older pictures, but with the 3/8 distance, it'll be 2 tapped holes going through them that start at the top of the frame, go all the way through, and those would press down into the brass shaft to tension down onto the chain. So basically, like to help explain it for how assembly would work, is it'd be the frame, these plates would go in with the sprocket and everything, then the chain would go on underneath, where at that point the sprocket would kind of just sit on top of the chain, not fully tensioning it, and then to get the full tension, the tap bolts will go through to hold it down. Then from there was a small skid plate design adjustment. Rather than just kind of being a big flat like L, it's more of a bit like slanted with some grading in.
So, in regards to the frame, not much has changed since PDR. We are using a series of 4 2x2 box tubes. The total width of the system will be 50.16 centimeters. The inner width will be 40 centimeters. Length would be 81.71. Height would be 6.35 centimeters. And then they're all going to be made out of 6061 aluminum. Aside from adding the dust covers and then for the ends of the box tubes and then also the access holes that aren't pictured there, the only changes that have been made are additional holes for the battery holder, the strap hinges on the back for deposition, and then as well as changes from how X-Step is mounting. As during PDR, X-Step was mounted on this front box tube here, but now is just mounted to the front section up here. Aside from that, nothing much has changed.
Similarly, not much has changed with the gearboxes. We're still going with the 1-to-3 gear ratio internally, but we're planning on testing that as soon as we can when we get to manufacturing. We also did mess around a little bit with the spacing with the sprocket to make sure they don't hit these riv nuts. But other than that, not much has changed. We also did actually redesign the gear or drive shaft to make this an internal thread instead of external thread, which just allows us to put a bolt in and attach the wheel that way instead of putting the wheel on and then nutting it on. It's just going to be a lot easier for us to manufacture. Other than that, not much has changed. We added dust covers. That's it.
Then just general extra overview. Our ground clearance and then top of frame to bottom of drive numbers have not changed since PDR. Our ground clearance is sitting just under 3 inches, and then top of frame to bottom of drive is sitting just around 22, 23 centimeters. These measurements were taken from, let me get a picture of the wheel. So these measurements are taken from about the top of the rim of the wheel, because looking at just pictures of how it drove in the regolith from Bama last year was about where it sat. So the numbers are a bit of more estimates, but they should be within a reasonable amount. Then our current drive system mass is 20.71 kilograms. That is slightly over what we had initially outlined with our system requirements of 20 kilograms. But I think, given the leeway, that's also, I think that mass number is missing a bit of adjustments with a couple small things. But we will probably be going over our estimated 20 kilograms from the beginning of the year. But I don't see that being as much of a problem, and honestly, we might end up having to put more access holes in the box tube for wiring purposes, so number is subject to change. But so then for our general manufacturing plan, most of it's going to be done in any machine shop EDC. For the box tube, it's going to be, and gearbox, it's going to be milling. Then occasional some parts are going to be laser cut. That's still a bit up in the air, but the gearboxes will be done first for testing like gear ratios and that purpose, and then going on to manufacturing the frame after most of things that are getting mounted are locked in, to minimize extra holes being drilled.
Alright,
So this is the updated DFMEA. The 3 to look out for are the ones that are over 100, and we're currently looking for ways to lower the detectability or the occurrence of these happening. So the first one is the frame yielding, which seemed to slightly happen last year. So we're looking to use FEA analysis to really look into that and see what we can do with that. And then the second one is the grinding of the gears. Since we used the chain drive last year, we think this is unlikely to happen because we're not even using the 90 degrees like we were last year. And then lastly, it's the gears stopping. And this is from sand entering. We hope that we changed last year from aluminum tape to properly rated dust prevention for that to occur. And further testing should help understand how accurate these numbers are.
Questions?
So FEA has been done on the frame yielding, which basically it looked like that was not going to happen. So that should drop the RPN of that one significantly below 100. The other two,
Yeah.
gears are funky. There's an equation that you can use to estimate if the gears are going to shear. Or the odds are those probably won't happen. But yeah.
Fingers crossed.
I mean, 6061 aluminum is pretty thick.
Mike?
So I'm still a little worried that we're switching back, like our threading method. Was that how we did it last year? Did we do internal or external threading?
External.
Yeah, I still think that if you just put a block on the outside, we call that the famous shaft collar. I think it's a lot less likely to break. It's a lot easier to manufacture. It's still about the same width. Just
So we manufacture beyond, what's it called, the back piece on the wheel.
yeah.
It's not called beyond.
I mean, do you do modeling on like wrench difference off the shaft? Like it's kind of rough. So
Maybe.
So what about sign?
Oh yeah.
It's going to be really, drill out that hole.
Yeah, exactly. I think it would be really easy to manufacture. I think it's a lot easier than threading other lines. Because we have broken threads both internal and external in the past. We did it one there. Didn't we? I swear we did that one year, and then we stopped. Or again, Joe went through to it. I'll talk about that. Also, the images make it really hard to like see like the specific design of the frame. Am I correct that you have like, is that 3 bolts on each side of a 2-inch box tube at the front?
Oh, here?
Yeah. Is that like a triangle of bolts?
Yes.
Yeah.
So you have 12 bolts attaching to the actual frame, 3 on each side and then 3 on each side. That seems like a lot, and it seems like those holes look close to the edge. And getting tools to tighten that, I feel like is going to be difficult, but it's hard to see without seeing a blown up view up.
Why wouldn't you weld it?
We don't weld.
I have a guy.
Welding's bad.
Why is welding bad?
Because the dimensions get really wonky, and we want things to be more in line and adjustable, because when our design is perfect,
Yeah.
the adjustability means a lot, and if we can't ever take this thing apart again, then we're not going to have a working robot.
Yeah.
There's a lot of adjustments that get made.
But, you know, I just wonder if we're finalizing the frame and you would increase your strength significantly if you welded it.
Caleb keeps telling me.
That depends on how good the welder is.
I don't know, I trust Caleb.
I should theoretically know how to weld, so.
were in Florida, we saw most teams sink and have problems with Drivetrain compared to Elegant. The stuff there was way fluffier and they were sinking a lot more. So if you can pull up videos from that here, I think that will impact how you're calculating your ground clearance in a very negative way. So if you can increase that at all, it'd be beneficial, but I know at this point in the process that's going to be a fun change.
Mike,
But it's worth looking.
what do you think about increasing the width of the wheels? Not the height or like the radius.
I forgot to ask about that. Your wheels are currently narrower than your trenching tool, right?
Yes.
If your wheels, with one side falls into a trench, how deep do trenches go? Next step.
4 inches.
4 inches? If your wheels fall down 4 inches, what hits first? And what does the robot look like? Is it able to get itself out of that, do you think?
What was our ground clearance?
It was
Like three. And that's bottom of chain guard gearboxes to like the inner rim.
When you say the inner rim, are you talking the aluminum piece or the white piece?
White. So
Basically, this part of the wheel at the bottom.
Okay, that's better, but
that
still.
was just what I was eyeballing.
Okay, it'd be nice to know if the robot sinks 4 inches on one side compared to the other, what's going to hit first, and do you think you can escape?
I think hitting first is gonna be chain guard.
either chain guard or the straight plate, depending on how it hits.
Yeah.
So if that happens, and now your other wheels are at a really bad angle, is there a chance the robot beaches itself? Because if that's a huge problem, then you have to let autonomy know that, so that they know, hey, you can never drive perpendicular to these trenches. You have to take extra care. So like that.
I don't think that driving, I would think that driving perpendicular to the trenches are probably significantly safer. I would say probably parallel is what's going to be the more dangerous one.
You think? But we already have to drive parallel. I'm saying you can drive completely back to the dumping zone and do your driving there.
Yeah, I guess, like, skew. I think that perpendicular, because the wheels have, like, what, a 12-inch OD?
Give or take, yeah.
And each hole is roughly 4 inches. So that'll probably be a drop of, like,
But
less
if
than
you're
a third.
perpendicular and you kick all material back that you're driving with, which is a lot easier because there's a 4-inch by how many inches wide hole?
4.5.
4.5. Then your wheels can go down suddenly, dig themselves deeper. And then I think, I don't know how you get yourself out of that. Because if you're at that crazy angle, I think going up is going to be a lot harder.
I think if you fall in a hole, you fall in a hole.
I think you're right. If one of the wheels slips into a trench, I think that because we only have like the 3 inches, so the bottom of the chain guard is gonna hit. Yeah. If the bottom of the chain guard is just flat on the side, I think we're screwed.
How much?
I think it's also because it's like the two wheels on one side are both like chained together.
Yeah.
If the front wheel is in the hole, like you'll still have the back wheel that's able to help because that will still be outside of it. So that can kind of help. I don't know what the like wheel to wheel distance is, but if it's like greater than that 0.7, that might mitigate the like beaching concern a bit.
I do not know this.
Whoa, go to the frame width. So I mean, outer width. So wheel to wheel probably like what, 5 centimeters maybe?
With the wheels probably takes a lot.
Guys.
Do you guys do the last two? I'm just wondering, like, if you have enough mechanical grip. The answer to the question is, if you have enough mechanical grip that you only have to use one motor, then that would answer your question if you can get yourself out of the trench. Because if you're only using one motor, then you can turn, even if you're at an angle. But if you can't with one motor, then you have to use both motors, and that's where you're running the problems. And that'll also solve your answer for your turning radius. Because if you're only using one motor, then you'll be able to turn a lot more efficiently than if you're using both motors. So I think once we get to testing, you should really take a look at how the motors function and how much mechanical grip that versus that amount. I think that'll answer a lot of your questions.
Yeah.
So just from the discussion of the I guess beaching on the chain guard, if that does happen and the chain guard ends up sitting on the regolith, it's made of lightweight polycarb. Is it able to take that, like if it does end up happening and it sits on the ground, can it take that, or would it experience it? Do you have concerns of it just breaking or something like that because of it sitting on the ground?
Based on the shape and material, it shouldn't like crack.
Yeah, it shouldn't like completely fail, but
it'll deflect a little bit.
Yeah.
But I don't think that the weight of the robot, since it's in a decently strong shape for hitting the ground like that, it should be fine, probably.
Like, if when we like each onto the chain guard, I'm not insanely worried about it like just buckling and failing. It would, like Kyle said, deflect a little bit, but based on just structure and then my bit of experience with polycarb, it shouldn't like.
It's also well supported by like the frame itself and the gearboxes because it's kind of wrapped around it on the edges. So unless the force is like directly concentrated in the middle, it shouldn't be a problem.
Yeah.
And even then, sand is, or regolith is kind of compliant and will kind of move out of the way before it.
I think that the situation, the beaching would be more concerning on one of the boulders. But
Avoid boulders.
As long as we don't like get stuck on a rock, it should be good. Any questions? Anyone?
Can you go back to your brass?
Chain control.
Yeah. Can you explain again why you don't want to use bearings here?
So this was a me and Kyle adventure. The idea was more, it could be switched into bearings if we needed to be, but
the concern is space.
Yeah.
There is very, very little space.
Because based on where it's sitting, like that's the reason why we had to not even use an idler. We just had to straight use a really small sprocket. Because where the chain is sitting now, it's either the sprocket, depending on its size, might end up having to poke into the box tube and wires are running through there, which that's not a fun combination. Or if we put it on, let's say, under the bottom length of chain, it would, depending on how long, depending how thick it is there, it would lessen our ground clearance even more. So, yeah, that was just the main hurdle design, which is why we went with the brass, just allowing it to be able to spin a bit better.
So why can't you put bearings in the two ends of it instead of like on the sprocket?
That could be, we could do that too. It's just, wait a sec, wait.
It's because the actual tensioning occurs by pressing down onto that shaft.
Yeah.
So that shaft does not spin.
Oh, the shaft.
Yeah. It's basically, it's going to be able to slide through these slots here with the bolts tensioning down.
How are you actually going to tension it? Like, how are you going to pull it down?
Pushing it down with bolts.
So the basic idea is that when it's initially assembled without being tensioned, this rocket will just sit on top of where the chain is, not really doing much to tension it. But once we get to that point, once we're tensioning it, it's gonna be, these are supposed to be a bit bigger, two bolts pushing down onto the shaft that will tension the system down.
The bolts directly push onto the shaft?
Yes. The shaft is not spinning.
So is this, okay, I'd like to see like a more finalized design.
Yeah.
So to be clear, in how it's currently pictured, the sprocket is inside the chain. That is not accurate to how it is going to be.
No, chain.
It's going to be on the outside.
Work in CAD,
It's going to be on the outside of the chain.
Stuff is phasing through things. The sprocket will be on top of the chain.
Okay.
Yeah. Chain and CAD's not fun.
The diameter of the bolts, how big and close are they to the chain itself? Would that does that cause any issues if the chain rattles sideways along the brass
it shouldn't rattle insanely amount sideways. But I think this is about tripled, just about there and there. Then the bolt holes, if it's 3/8, we're down to like a quarter maybe. It should be okay. This will probably involve a bit more actual testing and then fully getting the design realized in CAD. That like end of final decision was made after the this was completed and put into pictures, so the pictures aren't completely accurate to what it's supposed to be. But yeah, that would probably involve maybe a bit of adjusting once the CAD is updated, and then a bit of testing.
And then follow up on that is how is the bolt? Is there an access hole on the top of that
Yes.
frame thing? Okay,
So it's basically this plate goes all the way up to the top of the frame, and then it'll go down from the top.
Do you plan on / could you put like are you gonna put spaces on that sprocket to center it, and then that would get rid of that issue of it laterally changing, or is the sprocket just gonna be placed on the chain?
Theoretically, the sprocket will be just placed on the chain, because looking at it here, it's a bit on the inside, but spacers can be put in. Those are just not 3D printed. We need to line it up better, but yeah.
That chain is already pretty well defined from the gearboxes, which do have spacers in them, so the sprockets in the gearboxes and the chain shouldn't be moving, and especially if this is tension, there shouldn't be much lateral movement. If anything, the lateral movement might be good for it.
We can go software now. We have a half hour before. Guess it's not even open.
It takes half an hour.
Yeah. Alright. We'll do software after we get back.
We can't leave. Yes, it's open.
I'm not leaving right now. Sorry, it was about 11 p.m. when I did this.
Hold on, then take the. Where's the computer?
It's a mouse.
Over there, yeah, mouse.
So the first thing we have are just clips from our driving test. So this one is going forward and backward. Then it that's a mistake. It goes forward too much. But then we send it backwards again. That's about it for this one.
Wait, before you switch over, just a reference as to what's happening. Gray is just ground we can drive on. Black is something it sees as an obstacle. And the purple thing is the path that the robot is trying to follow. And this base link thing that moves around is where the robot thinks it is right now in the map.
This is the same one. There we go. This was one that didn't mess up, so this is sort of a success. We just have it going forward and backwards. As you can see, there's not really too much trouble doing this. We're playing it again. This is a crash, but we put it in there just to illustrate what happened, kind of. So we start going forward, and then this is a glitch. It disconnects right into the bucket, but we were able to recover by sending it backwards, was the idea.
And also the robot didn't really even notice that it crashed into a bucket, aside from the fact that it just pushed the bucket a couple of feet forward.
The last one is an orthogonal test, so we test basically how it can curve, and in this case go sort of around the bucket. And this is sort of a big milestone because we had to work with the limitations of the hard sand, getting the turning right,
and that's with the combination of both MPC and the differential drive controller getting the wheel spinning at the right speed in order to make it to the sort of other end of this path. Yeah.
Also, you will notice a large black line here. We didn't notice until after we came back, but the robot was seeing the volleyball net that we were testing on as an obstacle because it was above the ground level. So if we ever go back, we will make sure that that gets fixed because there will not. I don't think there will be volleyball nets hanging over the pit competition. Hopefully.
Yeah. So it's our first sort of successful autonomous navigation test, basically. Straight lines were pretty good, and tighter curves were a bit slower, but it was able to do it. We found that our sort of safe straight linear speed during our autonomous navigation was around 0.3 meters a second. That's the straight line speed. That doesn't include making any complicated turns or whatever. And then we're hoping that with higher torque motors and then being on regolith instead of hard sand, we can basically take tighter curves and maybe turn in place better. We'll want to do more testing, obviously, with new motors and in the pit and such. Path planning, it was fast. You saw there was one bug where the path canceled and we kept going forward. That's an easy fix. We're already aware of that, obviously. Yeah, that's in behavior. For SLAM, we're also another point of the test was to test how SLAM works. So it was pretty good. The best accuracy and clarity we got was around 3.5 meters. It can see even more distinct obstacles from even further if we need to. The full range this is an estimate on the flat surface, was around 4.5 meters, and the update rate was around half a second to around 0.5 to 1 hertz. So with this sort of information, you can conclude a sort of theoretical max speed of like how fast should we keep it under in order to not run into things of 1.75 meters a second, which is not an issue because with the current speed limits, the manual control max linear speed is half a meter a second. Yeah, but it's going to be kept lower than this theoretical max speed, as I said. And then the obstacles we tested were all sort of distinct. You saw the green bucket and then the volleyball net. In the future, we'd like to do more testing with less distinct obstacles, maybe like rocks or something shorter, basically. For future plans in terms of driving and navigation, we're going to investigate flattening the map, as Alex said, to determine what height we want our obstacles to be at. Increasing the SLAM update rate. There's a parameter we can look into changing that hopefully help it update even faster if we need to. And then another thing is investigating smoothing the path or sort of changing the working with the orientation and the curvature to make sure that instead of doing that sort of turning you saw, we can hopefully have more natural paths that are easier to navigate. And then the last thing is the bug where it stops on an empty path. Behavior. So our plans are working on this concept of operations sort of document. We're going to probably do it as a state machine. These are two ideas of specific implementation, a sort of global state topic in ROS, which is the operating system that has loops, and then other parts of the system will send it feedback when to change, or a set of tasks and command that will automatically sort of trigger each other next when they're done. Our first goal is one full cycle autonomy run for behavior. So that would be initialization, driving to the excavating a discernible amount, which is how they specified in the rule book, and then driving back and depositing it. And then after that, we're going to start, if we can get that working, start looking into full cycle considerations. So planning out trenches, longer trenches, maybe seeing if it'll work over the entire 15-minute or 30-minute game period. These are the list of like the remaining tasks sort of individualized that we need to implement for behavior, just for kind of reference. So you see the stuff we haven't done yet is the April tag detection, picking excavation zones, the sort of transitions, and some of the changes like stopping on mapping, changing, and detecting if we're stuck. And then this is sort of a abbreviated version of a testing schedule that we came up with. You can see at the beginning, it's sort of the subassembly. We're doing hopefully some tests then. During full assembly, I'm pretty sure the robot will be taken apart and put back together, so we won't have the old robot to test with, so we're going to work mostly in sim. And then from then on, we're going to keep testing the future behavior and stuff.
We're using ultra-wideband sensors as a way to help tell the robot where exactly it is, just in relation to the berm. And so far, we're using trilateration to figure out exactly where the XYZ position of the robot. And so far, it's accurate to about 0.1 meters in simulation and that is using accuracy that we observed from our real UWB sensors. At some point soon, we will actually be testing this accuracy with the real UWBs and seeing what values we get. And that value might be improved with a little bit more effort, but it is unlikely to change by too much. We also experimented with switching to a different ultra-wideband sensor that would give us a much, much faster update rate, up to about an order of magnitude faster. But that ended up not working because they ended up being a lot more inconsistent and just didn't work half the time. So we may return to those, but probably not, at least not this year. It may be a next year issue that we may come back to at some point.
So the encoder that we're using right now, it's capable of recording at 96 pulse per revolution, up to 4,096 pulse per revolution. We're currently putting it at 200. By the way, a pulse per revolution just tells us how accurate it is at counting the rotations of the motors. We currently put it at 200 simply because we think that's sufficiently accurate for us for whatever purpose we're going to be using for these robots. When we put it at the maximum resolution, it turns out the testing rig, our Arduino, is getting overwhelmed by all the data. So obviously we're going to need to do more testing to see whether or not it is sufficiently accurate or precise, but as far as we're concerned right now, it is. The benefit of doing it at a lower resolution is that we can handle higher RPM. At the moment, the encoder's technical spec sheet is saying that at 200 we can handle I think a maximum RPM of 8,000. Yeah, I don't think anything on this robot is spinning that fast. Yesterday night, you may have seen us just asking around, I think, Drivetrain and Xstep, just roughly how fast you think your motor is going to be spinning. I think we are relatively confident that it can handle up to 200 RPM. If there are anything that's spinning faster than that, so please let us know, and we're going to need to do more testing, obviously not with this rig. At the moment, we're using a Arduino encoder library, which by our testing, which is limited, but we're getting pretty accurate rotation measurements. We're certain that if we are kept under 200 RPM, which is what we think our hand crank is about maximum like 200 RPM. Yep. If we keep it at that, there should be no problem. And the next step is obviously we're gonna take this off and mount it on actual like some sort of power drill and just spin it faster and see how fast we can push it. If there are any necessity to increase the RPM, we simply just lower the resolution to 96. Yeah.
Alright, for current limits. So since this will be running on the TNC, it will be real time. And then the current limits are determined from previous year's data. So this was last year's comp data. We can see that this the red is an excavation motor, so that's running about 10 amps. So we set that as 10 amps. Wait, hold on, no. No, that's running at 10 amps, and then the drive motor here is running about 4 amps. And then we set the stall limits as 7 amps and 25 amps for each of the motors. So we should never really hit them, and then if we do hit them, something has really gone bad. And then for the current regulation and recovery, we have this running both when it's on manual control and autonomous, so nothing goes bad. And then basically the way it works is if the current limit is hit, we will stop motor operation, and then if it's on autonomous, we will have a retrace its path for a couple of seconds backwards, and then or resets the position. And then if this after a couple tries of autonomously, if it keeps filling, we will switch it back to manual to hopefully fix the problem. Since our guy isn't here, I'll present telemetry. So we currently have 3 different layouts. One for drivetrain data analysis, one for Xstep and encoder analysis, and then one for the general GUI. So for the drivetrain analysis, we will have a graph on the left showing just 2 currents for one for each drive, and then this is the same, and then that's just the actual, well, if it never loads, but if it loaded, it will be just different value states that the robot's receiving and sending, and then here will be a actual video of the robot running the footage. The telemetry has the excavation have a similar GUI, and then up there it's just showing the excavation excavation current and the encoder degrees, and then yeah, just similar layout. And then for the general GUI, this is really just a rough draft.
I do actually know
Okay.
what all these are.
Okay.
So up here is going to be the three UWBs and their raw distance values, just to help us troubleshoot any issues if that arises. I believe this is either current or position, depending on what we need for each of the motors, or can be repurposed for something else, because those are already covered in the other 2 GUIs. Just a quick overview of all of the important robot currents, in case so if one of them spikes too high, we can stop that. And then this is a simple diagnostics tool where we can input a bunch of messages that are just hey, is the controller connected? Is the robot stuck? Basic things like that. Down here is another empty spot that we can fill in later, and this is a 3D model of where the robot is, of where the robot thinks it is, similar to those videos that you saw earlier. Any questions? No.
Can you go back to the current slide? The one after that.
This one?
Yeah. So when you say current limit is reached, are you talking about stall current or normal?
Stall current, the ones that we determined.
Do you know if we hit a hard, because my understanding is for excavation, you might want to just use current for hard stop for the linear actuators, right? So do you know what the what that current spike looks like?
For the
if you hit a hard stop, do you know what the current spike would look like? Because I want to make sure we can distinguish a hard stop from an error.
So right now we're just doing if we hit the current determined on the previous slide, we just stop.
So for the linear actuator side, they have internal limit switches.
Oh, they
basically, so their current will be 0 when we hit a hard stop in linear actuators, and the linear actuator internal hard stop will hit before the system hits itself, if that makes sense.
Okay, so linear actuator will stop.
So linear actuator will stop itself, basically. But we should make sure on the software side that for autonomous linear actuator, like plunging and stuff, when we do that, that we should be telling it to move and then waiting for it to we have a 0 current, and that's how we know that we've made that hot stop.
Okay, so 0 current is equivalent to hitting hard stop.
Yeah, because it'll shut itself off basically.
Alright, sounds good.
Yeah.
Yeah. So you said that the accuracy of the position of the robot is 0.1 meters currently, give or take. Is that?
Yeah. So that's the UWB sensors. I think SLAM is. Actually, what do you know what SLAM's accuracy is positionally?
It's good enough.
Yeah. That's the important metric there.
Okay, so it's good enough that you're not concerned about when you're going to trench that it won't deviate off too much and get the wheel stuck in the.
That's correct.
Yeah. Okay. And then I guess follow up question is just I noticed that the bandwidth estimated bandwidth that the robot will use has increased substantially since PDR. Are you guys, do you know what caused that, and is that going to continue to increase, or would that increase from like affecting the SLAM? If you need to increase the update rate, would that increase that?
So the biggest contributor to high data usage rates is us streaming video back to ourselves, and if we can avoid doing that, that would significantly reduce our bandwidth. At the moment, we still need to do that, so at least for driver control, they can see what they're doing, and it's also we can troubleshoot. Although ideally, by the time we get to competition, our autonomy would be good enough that we can stop one or all of the video streaming.
So when you say increase from PDR, I've only created the one data bandwidth estimate. What was the one from PDR from, like last year, or?
It was a rough estimate that we came up with.
Yeah. So all I know is the picture we provided was from the most recent test. I don't know what the previous sources were from. I don't know like what the difference is.
That was probably us.
And on the previous, like the test that you had, that was on what were we streaming back? Were we streaming back video?
Yes.
Video footage?
Yes, we were.
Streaming? Okay.
That's probably where the vast majority of the 600 kilobits went to.
To not showing back video, but only like would we still be able to stream back like 3D mapped and all that stuff? That
Probably.
a lot of data usage?
It is probably going to be the next largest data usage, but it's also, I believe, going to be significantly smaller than a raw image or a raw depth image. Yeah.
We were talking a lot about earlier about potentially the robot getting beached or stuck, or stuck on some sort of obstacle in the course. Is there a way for the system to like detect that it's stuck?
Probably with current, right?
Yeah, just current limits. Right. Well, like if like a wheel gets stuck and it's just like kind of like the right side gets beached and the right side is just spinning, but in like free spinning, is there a way for the robot to be like, I'm not moving and I should be moving, or?
I think there can be. We could also, in the same way we have a current over limit, we could also have a watcher that just looks and says, hey, we're spinning at 100% power. We are drawing 1/10 of an amp. That's not right. So we could do that as well and just look for any abnormal current spikes in both directions. Yeah.
So in that video, the test you showed, is that just localizing with the camera, or are you using ultra wideband?
We're not using ultra wideband. That's just SLAM from our depth camera.
Wideband means wide camera.
No.
Wideband's a little sensor, you can say.
They're little sensors that they're ultra wideband because they emit across a large range of bands. You can imagine them as basically very weird and specialized Wi-Fi transceivers because they're pretty close. Yeah.
And then, so what are you using the wheel encoders for? To like determine how fast the robot's going?
Partially, and we can also use it as an extra source of error if we see, hey, we told the wheels to spin, and the encoders aren't actually moving at all, then that's an issue.
Yeah, that's sort of what the PID is.
Or alternatively, the encoders could be like spinning at a full speed, and
Yes.
or you don't need the text, so we're not moving anyway. That's
Yeah.
also stuff.
And also, what we are using them for right now is that we have a PID controller on each of the motors, so that if the sand or the regolith gets slightly denser at one point for whatever reason, or there's a small divot because we drove over that area before, it can compensate and still keep going at around the same speed instead of just spiraling out of and just not producing enough power to move the robot.
I almost wonder if it's better that it keeps moving even if it hits in a divot, because at the very least it'll have a chance. Because if it's still moving, then it has the velocity to exit.
That's the current theory. That's what the current is, that we tell it you would like to move forward at 1/4 meter per second, and we'll say, okay, I'm going to move forward 1/4 meter per second until it's sending 100% power to all the motors, in which case it can't go any faster, and then we have issues of our own because it can't get out of that. Yes.
Does the robot know its orientation?
Yes.
Just through the camera?
Yeah.
Through the April tag.
Well, April tag and also SLAM does give it an orientation and position of where it is.
Yeah, rough.
Very rough based on previous time.
Do GPS.
Explicitly disallowed.
We just need to put a GPS constellation around the moon. Easy.
It's just that we're working on GPS relative to Venus.
Okay. Yeah, I think so. I don't know if anyone has any more questions.
Alright, cool. We'll break for lunch and then we'll be back to the
I don't know.
Last year,
you guys can just, instead of like saying you guys can just like say
I applied to like 4 missions.
Alright, we good to just go?
Yep.
Can I just click on using the mouse?
Yeah, mouse should be still.
Okay.
It is like not a really fun process.
Alright, hello everybody, and welcome back to the P&H portion of CDR. We'll try and get you guys out of here as quick as possible, I suppose. So just jumping right into it, this slide details the system architecture that we have this year compared to last year. We've kept the buck converters that we're using specifically to convert the 24 volt input from the battery down to 5 volts that power the Jetson and the encoders. We're also keeping the same hardware for the power meter and e-stop, which is NASA mandated, and as of right now, we're keeping the same motor controllers and then just having backups. And then we replaced a lot of the safety components like the main fuse, the breakers, and the relay, as well as the current sensors, the teensy board, and the battery, and I'll elaborate on all of that later. And then we also added under voltage protection to prevent us from over discharging the battery, and then a power distribution board with a hardware shutoff to help with wiring and then provide software with some additional functionality. So moving right into the battery selection, the main reason that we're replacing the battery is because the competition runtime increased to 30 minutes. I forget what it was. I think it was like 15. So like basically doubled the runtime, which it necessitates a size of the battery. And the batteries that we had were already kind of small to begin with. So the other issue that we were running into last year is that for a 24 volt LiPo battery, the maximum voltage that it charged to is about actually 26 volts, which was too high for the motor controllers. And so we had deliberately discharged it a bit so the voltage would drop, where we could actually turn on the motor controllers safely. And so the desired changes then are an increased capacity and a lower maximum voltage. And so to calculate the capacity, I was given these values by Kyle here, and it's the estimated motor run times. So combining that with the power draw of each motor, we were able to determine that we need about 3.6 amp hours per run, which includes a power budget for the Jetson, as well as power inefficiencies caused by the lower voltage, as well as just losses in the wire due to heat and everything, and all the inefficiencies of the electronics and stuff like that. And so what this results in is moving from a 7S to a 6S battery, which has a 25.2 max voltage, max voltage, and then moving to a 13 amp hour capacity battery, which should be good for 2 runs at a 2x safety factor, meaning that around 4 runs should fully discharge the battery. Yeah, so that's the battery. And then moving on to backup motor controller selection, the team kind of narrowed it down to these 3 different choices based off of kind of different criteria. You can see that the max current is pretty different for all of these, as well as the max voltage. Max voltage is a little bit different. It just means that all of these motor controllers are compatible with the battery as is. The requirements for these motor controllers to be drop-in replacements for the ones we have would be that they're dual channel, meaning it can run 2 motors off of 1 motor controller, be communicated using a serial protocol, and then the appropriate max current and voltage for the motor. We're leaning towards, obviously, the most expensive one here has a max current and voltage and everything that would be able to handle whatever we could really throw at it reasonably. But it is the most expensive, so like if the motor controller that we were using for Drivetrain burns out or something, it might be more beneficial to buy a cheaper motor controller that would, because since we don't need that max like 50 amps of current, since both drive motors like while both stalling would draw like 16 amps max or something like that. So speaking of stall current, onto the breaker selections. So the reason that we're replacing these is because the old breakers did not factor in like the varied times to trip, and then we have updated max current draw from the current sensors and stuff from last spring, and so using the updated data we can then choose new safety components. And so moving into the requirements for each breaker, the X-Step motors have a peak of 35 amps stall current. The drive motors peak at 8.67 amps-ish. And then we'd like to have a trip time of less than 5 seconds, because any more and you kind of like defeat the purpose of using breakers to help save your motors. And then the main thing that's difficult is that trip times vary widely, and an iterative testing process may need to be used to kind of hone in on a specific value. And so then elaborating on all of this, for the drive motors, we've selected a 5 amp breaker. When you see like a 5 amp breaker, a breaker is designed not to trip when you're just like shoving 5 amps through it, and the trip times are very dependent on how much current you're shoving through it and the temperature of the surroundings of the breaker. And so with a 5 amp breaker, nominally we should see around like 4.4 amps. If one motor is stalling, we should see 4 to 40 seconds trip, and then if both are stalling, it should trip in 1.5 to 6 seconds there. And then we will have to do like testing on this to see if we want to like change these values at all. But this is kind of like the best we can come up with when dealing with these like pretty large bounds. And then so similarly for X-Step, a 12 amp breaker is chosen. Each X-Step motor is paired with an actuator, which adds like a nominal current of about like a couple amps, which is factored in there. So nominally there should be no trip, and then when the X-Step motor is stalling, it should trip in 1.5 to 10 seconds, which will of course have to be validated experimentally. Then for replacing the relay and the main fuse, so first we need a relay that can be PCB mounted because of the motor shutoff on the power distribution board. So that was one reason. We also wanted a relay with a higher max current. I believe at one point last year or the year before, we like accidentally like shorted the battery or something like that and like melted the relay totally. So this relay should be a little bit more resistant to that because it's rated for 100 amps of current. I really couldn't find anything much larger than that without dealing with, you know, a really huge increase in cost and size. And then the main fuse value needed to be lower for the same reason as the breakers. If you know our main fuse is taking like 30 seconds to trip when we're shoving 100 amps through it or whatever, that's a pretty useless fuse. So yeah, then this is the timings for the fuse stuff. The graph on the right is showing the trip time versus the current. We've selected the 60 amp version of the fuse so that it should trip quickly at around 100 amps, which is what the relay is rated for. Yeah, and then theoretically the system should only pull over 60 amps during a battery shorting or multiple motors stalling at the same time. So the fuse shouldn't just trip for no reason. So on to some of the more custom boards. This is the current layout for the power distribution board. The purpose of this board is to mainly reduce the wiring inside the box, utilizing the space more effectively. So we have like a single 24 volt line coming from the battery, and we need to split that off into all of the motors. And this PCB basically does that. And it also allows software to cut power to the motors without killing the Jetson, which is this circuitry here. And then we could also have placed this board. We could place the board. I meant to say after the motor controllers, but that would defeat the purpose of reducing the wiring, since we would have to still break out the connection from the single 24 volt line manually, which would make the whole space saving effort kind of redundant. But it would require us. But it would the benefit to that is it would allow us to use one breaker per motor. But based off what I've presented previously, I think the breakers are able to do their job even while being one breaker per motor controller. And then so just what you're seeing here is this is where the relay is going to go. And then this is a signal that's going to be input from software. It's just going to be internally in the box from the Teensy. And then this will cause the relay to trip and allow current through. And when software, I think, like deasserts that signal, it'll switch the relay off, preventing current from flowing. And then these spots are where each of the breakers will be, and then this will be where the wires will then go out to the motor controllers. And then the back side of this has the like X step out minus, so the other polarity of the connection. All right. Next, this is the under voltage protection board. It's being worked on by one of our members as part of their senior design project, and it essentially prevents us from over discharging the battery, as I mentioned before. Here, it'll take an input from each of the individual battery cells, and then this main IC will essentially do some processing and then send out a signal that'll go through this circuitry here. Then then this is connected to the relay. So that's how that works. And then the current sensors.
So last year, the current sensing was basically done through I think it was like 6 or 8 independent boards that we ordered and just wired together. Yeah.
So the boards basically made a big mess of wiring, as you can see on the left there. That's kind of the end result of just like 6 or 8 boards that were all a big mess in the box last year. So this year we're basically taking the same some of the same ICs, some of the same purpose ICs, and putting them into the design on the right. Each of these pairs of squares here will represent one motor. So the wires for the motor go through the holes, one for the positive, one for the minus, and that measures the current. And it goes through 6 ICs up here, and then these are current sensor ICs that will represent the current values of voltage that gets sent down to these 2 ADCs, which will be able to communicate to the Teensy through this port and send, software will be able to access values for all 6 of the motors through that.
Okay, so moving on to our custom Teensy board. So we decided to change up the design for it this year. From the previous year, and we have like a bunch of reasons for that. One of the main reasons is that we're adding like an intermediary cable between the sensor bulkhead to the Teensy board. I think this is just mainly for like organization, just like not restricting where the Teensy board will have to be placed in the P&H box. So it's for easier access and things like that. And one thing we're also trying to do is make sure that the wires coming out of the D-sub are like grouped together so they each go to specific sensors, just for easier removal and testing purposes during competition time. So and we have like more new encoders that we're using. So we're using digital encoders. So we had more signals for that. We have the UWB, which goes to the teensy, as well as some load cells. So this is kind of like the input to the box from the D-sub. As you can see, we have grouped like we've grouped like the separate sensors together, like the encoders, and then the load cells, and then the UWB. So then this is what we have currently for the layout. So on this side here are all the encoders, and we have the load cells down here, as well as the power port, as well as the 5 volts and the ground, and we have the UWB down here, as well as the main teensy. And these are where the motor controllers are attached, and we have over voltage protection for those, as well as the UWB, just to make sure that nothing gets fried, hopefully. And we also have the current sense board over there. So yeah. Is that it? Ooh.
No, that's not it.
It glitched.
Just go to the
Scroll up.
Yeah, scroll too.
So this is what the preliminary idea of the wiring paths from the e-box to each of the motors is going to look like, utilizing the channels and holes that are in the frame to route all of the wires, basically. And so this is the general idea of how the wires are going to connect to each of the motors there. Not too much else to say for that. And then finally, our next steps are going to be testing the safety components. We ordered a high current power supply that should arrive on Monday for us to test those. And then I just ordered all of the custom circuitry, so that should be here by next Saturday, and we'll get to putting that all together, soldering that all together, and then testing it. And then obviously we have the assembly and testing of the integration of everything within the box, and lots and lots of debugging. Any questions?
If one of the breakers or the main fuse trips, what happens after that?
Yeah, so the breakers are I forgot to mention, the breakers are auto reset breakers, and so the breakers will reset after a certain period of time. I don't know what that is off the top of my head.
Short enough to use within competition? Like if we trip
It should be,
okay.
yeah. But I mean, we'll hammer out time while through testing. That'll be part of it. I don't even know if the time is mentioned in the data sheet. But anyways, but they should reset the main fuse. If the main fuse trips, there's no hope. It's everything's dead. But again, the main fuse should only trip if something is going horribly wrong. Like if the battery shorts, or if like the motors are on fire or something. Yeah. Other questions? Yes.
I noticed that could you go back to the motor wiring?
Mm-hmm.
I don't see a plan to connect to the deposition motor. Is that because you didn't know what was going on? What can I do to make your job easier there a little bit? Purple wire?
Yeah. That's right here.
Okay.
So it should just pop out the side of the frame.
Yeah,
it'll
it'll
pop off and just do a
yeah,
little
pop
jump
off into the side. Yeah.
Alright, thank you.
Yep. Other questions?
So looking at the stall,
Mm.
you had said that for the excavation and auger motors, that it's approximately, what was it, 30 seconds of the stall current to trip? Or no, it was a short period of time.
For this?
Yeah. It's a short trip time for stall. What I'm partially worried about is nominally, or not really nominally, from last year's data, when under load, excavation was drawing like 20 amps.
20 amps?
Is there a risk of the breaker tripping when it's not supposed to? Because I would assume at 20 amps.
Yeah, there's a risk.
So
there's a risk, and I think this is something that we can hammer out a little bit more clearly while we're testing, just because like these times, like how long does it take for this breaker to actually trip at 20 amps? You know what I mean? Because like based off of this, right? If this is a 12 amp breaker, like you're looking around like here, like ish. So it could be from anywhere from like, 10 seconds to, well, doesn't trip. Like it's only when you really get to like 2 times the rated current. So like if you were shoving like 24 amps through this breaker is when you would get more reliable trip times. And that's true for most of the breakers and fuses. Once you get to like 200% of the rated current, then you're getting more accurate trip times. So stuff like that, and it might vary like at an environment level. It might even vary at like a component level, like the way it's like manufactured and like the how are there like flaws within like the material that's in the breaker and stuff like that. And so we can hammer that out when we're testing, and we can always up the size of the breaker if it's a concern. Other questions? All right, I see none. Thanks.
Alrighty, so that's CDR. We're pretty much done with design. There's a couple more things on the mechanical side that we got to touch up, and probably a couple of things that is worth looking more into based on this feedback. But thank you guys all for your hard work over the last semester and this. Well, I think we're moving on a very good track in comparison to previous years to manufacture this robot in time and have a real good shot at competition. So looking at our schedule moving forward, I touched on this at Tuesday's meeting, so I won't go into too much depth. But our next major deliverable, we will have TRR, which stands for Test Readiness Review. So that's basically once the robot is built, we just want to make sure that really it should be a fairly short presentation where this is our testing plan, this is what we're trying to get out of our testing, and what kind of risks do we have?
Talk about that a little bit. Yeah, so actually that one, test readiness review, so typically in industry that's something where it's like before a test you look at it, a major test. In this one, our major test is going to be proof of life, and so that was supposed to be like a preview of like things that we need to get to before hitting proof of life, and that was supposed to be just a leadership one, but we can do a whole club just for the kicks of it if we want. But yeah, the whole purpose of that is are we on track to hitting proof of life? If not, what do we need? And then also new this year would be like a plan going into proof of life, making sure we have people, places, and equipment ready for doing that proof of life video and getting it turned in. So that's what that would be.
Yeah, and our proof of life is going to be April 3rd. So that is going to be our most important deadline. If we fail to meet that one, we will not be attending competition. So submitting a video of the robot overgoing all its phases of operation, whether that be manual or autonomy, we'd rather it be autonomy, but manual is perfectly fine for the purposes of that deadline. Basically, in case you guys, as a reminder of the rules, NASA hasn't given complete guidance on like what is go. They said they're going to send out invitations to come. So we just have to be one of the top probably like 20 teams, which assuming we are able to output a proof of life video, we will be. That is the hottest deadline of the entire year, is that proof of life deadline for the majority of teams, unless you're Max and have to suffer through systems paper. But yeah, this is the remainder of the schedule. This is the end of CDR. And that's it. Thank you guys all for your hard work. We're getting there.